RÖFIX SismaCalce system. Earthquakes are geologically induced vibrations of the Earth, which can have devastating consequences in some cases. The violent shock of an earthquake comes suddenly and unexpectedly, most without warning. The ensuing damage and destruction are dramatic, not to mention very high number of dead and injured. In order to ensure adequate protection from earthquakes in seismically active zones, appropriate earthquake-resistant standards must be adhered to in the planning and construction of buildings. Not only new buildings must be constructed in accordance with appropriate standards, but also the safety of the many old buildings must be urgently improved. Masonry buildings, dominantly with no or low code implemented, still represent a great majority of residential and public building stock in many earthquake-prone countries. The structure with unknown level of seismic stability have high potential to be severely damaged during strong earthquakes. As a solution of the problem, RÖFIX has developed the innovative system RÖFIX SismaCalce, a system that combines a reinforcement of masonry with a complete insulation. The system brings structural improvement in a building and represents a single system which brings improvement both in terms of structure and energy optimization. It is the first time that these two features have been put on the market. Hence, an intensive test campaign was necessary in order to understand the behavior and optimize the system in the best possible way. The laboratory tests carried out at the Karlsruhe Institute of Technology showed a demonstrably high force distribution of the seismic energy, improved ductility and the reduction of the tensile load on the masonry. The Faculty of Civil and Environmental Engineering in Padua executed a series of further experiments for the evaluation of the performance of the system, in particular with regard to the problem of non-bearing walls. The strength, ductility and strength distribution were tested, as well as the stability at maximum deformation capacity after previous damage by loads below the maximum deformation capacity. The tests that we have carried out are two experimental tests. These are combined tests conducted in plane and out plane to check the behavior of masonry veneer wall. In this particular case, the test is a full-scale one, conducted on a sample which reproduces a span of a real structure. We can see pillars and the upper and lower beam connected to the workshop ceiling. Inside is a 12 cm thick masonry veneer wall made with horizontal external masonry. The two tests have been conducted on an unreinforced masonry and masonry veneer wall reinforced with special plasterwork instead. The internal example has a mesh, such as to reinforce the masonry veneer wall. To investigate the efficiency of the innovative methodology for seismic retrofitting of traditional masonry building using system RÖFIX SismaCalce, an experimental studies were realized by the Institute of Earthquake Engineering and Engineering Seismology Skopje. The quasi-static tests on numbers of wall elements showed that retrofitting contributes to significant increase of elastic limit, tensile strength and demonstration capacity of the walls. These results were prerequisite for correct further analysis of the scaled model, as well as for interpretation of the model behavior. We have paid a lot of attention to the construction of the model, the construction and testing of the wall elements, and the first results were unexpectedly successful. So that surprises us, because we have a different understanding of the efficiency of composite materials in seismic upgrading of masonry. They are good. They are superior materials, but for seismic upgrading of masonry, it was believed that we need additional elements to dissipate seismic energy, like reinforced concrete elements, which efficiency was proven during earthquakes. Their implementation in existing structures is, however, completely different and more complicated in comparison with what was proposed with this project. There is a need for incorporation of reinforcement, and you have to go under the foundation, etc. That is why we had, let's say, slight doubt. However, during actual compression testing of the wall elements, we have seen that the applied force grow and grow, and we could hear glass fiber breaking, thus dissipating the induced energy. So this is what practically proved that Professor Stempniewski was absolutely right, and what we got convinced of. Shaking table testing of a 1 to 2 scale model of a hypothetical masonry building has been performed both in its original and retrofitted state. The models were tested under 3 types of earthquakes to predict the prototype behavior under different earthquake conditions. The models were subjected to the same experimental program. However, due to the obviously higher resistance of the retrofitted model, the tests continued under higher intensities of input excitation. Comparing the levels of maximum applied effects to the original with 0.35 G and the retrofitted model with 1.22 G points out that for about triple excitation level, the damage level of the repaired model is considerably lower. The overall stability of the model structure was not affected, and the experienced damage level is not beyond repair even for the highest intensity of input excitation. Each test course brings uncertainties, but there is of course also a certain tension before, about how the other ones will look at it. But that was just awesome in the end, to see it live, how it works, and just to feel as the energy then acts upon the building. I believe that is simply the impressive thing with such a shaking table test. You have to see clearly if you think about it. If now the real earthquake had occurred in Skopje, many buildings would probably have been destroyed. And for this one, we need a bit of color, and then it is back intact. And I think that's just the crucial thing today. On the other hand, I'm a little disappointed. I still do not know to this day where the limitations of the system are. They have not been found yet. The RÖFIX SismaProtect earthquake protection multi-axial fabric is a hybrid fabric of special alkali-resistant synthetic and glass fibers with a coating to offer an optimum fiber mortar composite. The earthquake-induced movements and energies in the masonry can be absorbed through the multi-axial fabric construction from all directions. Forces and force peaks are distributed in this particular tissue and additionally reduced by the special fibers. The fabric is alkali-resistant, corrosion-resistant, easy to handle, and can be embedded in a form independent of all masonry creators. The earthquake protection tissue SismaProtect is processed in connection with the RÖFIX SismaCalce embedding mortar on WC/NHL basis. This is characterized by high ductility and low modulus of elasticity and perfectly adapts to the different requirements of all types of buildings. The reinforcement layer of the system RÖFIX SismaCalce has very good adhesion and vapor diffusion permeability and is ideal as a base for the various RÖFIX thermal insulation composite systems. The thermal and seismic renovation of a building with RÖFIX SismaCalce brings many advantages and benefits. Earthquake-resistant protection, improved stability and ductility of the walls, higher stability and consequently less risk of structural collapse on the non-bearing walls, reduction of the energy consumption of the building, elimination of thermal bridges, use of heat storage of the walls, uniform heat insulation and facade protection, healthy and improved comfortable room climate, cost-effective renovation measure and increase in property value. Spray on at least 3 mm of plaster. Embed the RÖFIX SismaProtect earthquake protection knitted fabrics in the fresh mortar. The lintel band is run like a belt around the whole house in the ceiling and in the floor plate region. Where the band is brought together or where it is extended, it should be overlapped by at least 20 centimeters. These are set diagonally and sharp at the lower edges of the masonry openings. The entire web is cut out and laid so that the balcony slab is integrated. In the fresh mortar, the surface reinforcement is vertically applied with 10 cm overlap. After all the fabric sheets are laid on the building, the reinforced plaster system is plastered with at least 5 mm RÖFIX SismaCalce. Thus, a total layer thickness of the reinforced base coat of at least 8 mm is achieved. In order to create a non-slip surface for the following constructions, the entire area should be combed through with a fine RÖFIX 16 trowel horizontally or crisscross, as long as the plaster is still fresh. This ensures fine-toothed grit grooves, in which subsequent layers of plaster can bond well.